First of all, thank you so much for inviting me. I love this workshop. I'm very much looking forward to hearing all the talks today. Super exciting, the combination, especially with policy and robotics and so on. So I'm excited about this very much. The other thing I want to say is this is a workshop, so I very much would appreciate questions along the way, discussion. Don't have to go through all my slides. If anything I say, you agree with, disagree with, speak up. Okay, so also, 9 a.m., some of you are jet lagged, some of you are grad students who do not wake up at these hours. So there's a whole bunch of kind of things going on here. So just really, the beauty of workshops is conversation. So the other thing I'll say is that I tend to do workshop talks in a much more loose way than I do kind of seminars or things like that. And even those are kind of loose. So yeah, so that's kind of the idea. So what I want to do is I want to kind of, this is the description of this workshop. And I want to kind of hone in on a few things from this description. So and kind of examine this. That's my purpose for this one. Okay? So this is the description. The first thing I'm going to pick on is the word safety. So there's the word safety there. And I was trying to think about what does it mean to be a safe robot? I want to kind of examine that a little bit. So the first thing I did was, let's see if we can get an image, right? So I went to ChatGPT and create an image of a safe robot. So it was very amusing. This is what I got, right? Safe, it's a robot. So I was like, okay, clearly I'm not the best prompt engineer. So I was like, okay, let me add a little bit more complexity to it and say, okay, people want to be safe, blah, blah, blah. That's my prompt. So my prompt is, people are worried about robots acting safely in the world and not causing harm. Create an image of a robot that is safe. So create a robot that's safe. And I was thinking about maybe refining the prompt a little bit more, and I was like, actually, no, this actually fits what I want to say. Because put a sticker of safe on a robot. What does that mean? What does safety mean? Okay? So, safety. Let me ask you guys a little bit. I'm not going to do this. This is the only time I'm going to do this. When I say safety in the context of robotics, what does it mean to you?
It depends on the context, like what the robot is doing.
Excellent. Depends on the context, right? There's no kind of global safety, right? So give me an example of a context.
Okay, I was supposed to only answer one question.
Okay.
I can help. I have been focusing on this question a lot since I graduated about a year ago and joined a technical consulting company. A lot of the time people will come to us and say, hey, this car did exactly what it was programmed to do, but someone still got hurt. Like, could you evaluate whether or not this is a safe system? And people will come to us all the time asking about safety. So I think questions are about safety are, does it perform as expected in normal situations, but also how does it fail is often.
Cool, so I hear the word fail and I hear the word as expected. So what is this as expected, right? So there's what does that mean?
There is a minimum in everything. For example, for a car, like it doesn't get you killed, is as expected, or doesn't cause damage to anything, is just the minimum that we expect.
That's a bit awesome. Yes.
Expected means if it doesn't happen and someone gets hurt, then someone else gets in trouble.
If it doesn't happen.
If something happens that is unexpected, then someone will be in trouble. That's the definition of expected safety.
Okay. So you're basically looking at it from a context of blame.
Accountability.
Fair. Okay. So I'm gonna. We had a workshop at Penn in February, so several of us were there, and then we had a breakout session with 20 people ish. Something like that, in which we wanted to define safety. And these are some of the things that came up. So constraints on a set of states, robustness to adversarial perturbation, absence of outliers, bad things do not happen. for the example of the car, right? I can build a 100% safe car. I'm just gonna put it in the parking lot and never move, right? That's safe. Is that what we want? I would argue no, right? So the question of safety is I kind of don't like the word safety, because the safety implies nothing bad happens. But we don't just want nothing bad to happen, we want good things to happen, right? So there's kind of questions of what does it mean? So I'm going to push back on a few things here. So the notion of safety here is what I'm trying to say here is definitely context dependent. That came. So XY, this is literally the XY of the table, and each point is the position of a block. The right-hand side, all the red both of them, the red dots are placements that were successful, that the robot was able to satisfy the specification. Black dots are locations that it failed. And what you can see here, and the blue is also successful. So just doesn't matter. The thing I want to show you here is that very quickly, the lighter the color, the earlier the sample on the left-hand side. So you can see it starts kind of everywhere, and very quickly it kind of gravitates towards the areas that actually have failures. Okay, so that kind of the probability of failure changed between those two techniques. But the kind of cool thing that this provides you also with examples of failure. So now you can start visualizing what these failures are. So I'm not reading anything into this. I'm not saying this is a global thing. But in this case, in this specific case, it was interesting to see that the two separations, there's like a cluster on the left, on the bottom left, and there's a cluster on the top right. The bottom left is the block slipping. So it's just falling off. The top right is the arm unable to pick up, to go above 0.5. So what am I saying something that it's always going to separate failures? Absolutely not. Right? But there's something here that allows us to kind of sample from different spaces and the uncertainty to see kind of the types of failures we can get. All right. I'm going to move on now to monitoring and repair. Any questions? Any comments? Anything you want to push back on? All right.
I think something we're going to talk about during the day is how do these different ways of visualizing and thinking about and quantifying the failure cases, how useful are they and how can they help advance the conversation? With something like this, I can imagine be extremely informative, not only to the engineers building the system, but to policymakers and the public and people making decisions about whether they want this system to be running around and doing things. But on the other hand, something like, oh yeah, probability of failure is 10 to the minus 7. I don't, what does that mean? Especially in a world where we don't really have good base rates for how often these rare extreme events are happening. So at best, I would say it's to some extent a bit of a, wild guess.
Well, two thoughts about that. So 1 10 to the minus 7. I mean, that's the way FAA works, right? So you have, or the way you think about safety in highways, you have miles driven, you have miles flown, you have all these kind of things. So that's where the number might make sense. But on the other hand, a number doesn't make sense here at all because I'm making assumptions here, right? In this case, I'm making assumptions on what is my distribution of noise. There are always assumptions. So I think the way I think about these things is when you have specifications, it requires you to be explicit about what is it that you're requiring and under what conditions. Because you have to make some assumptions. So here, again, very simple example, not interesting, blah, blah, blah. But here, the uncertainty is where's the block? So that's my world. The block can be between, I don't know, whatever, 10 centimeters. No, what can I do? I feel like something is up right there. Whatever, the table. That's my whole world, right? If the block is, if I add like an extra side table to the side, I don't know. I have no idea, right? That's not within kind of what I'm thinking of. So this we're building the toolbox that, given a specification, given assumptions, allows us to say things. Now, this given a specification, given assumption, that's a strong statement. And you have to start thinking about what that means. And we're going to get to that in a little bit. But yeah, the more we're clear about specification and specifically assumptions under which we do these things. Even if you think about kind of safety engineering, right? So when you build a system and you estimate the risk, you're going through this kind of scenario and you're modeling everything that could go wrong and all that. These are all assumptions you're making, right? In any case. So here, just being explicit is useful. These techniques are useful in being explicit about specification and the assumptions. Okay, so monitoring and repair. This is kind of I want to talk a little bit about this. And again, that's the Adam. And Jen was not here today. So what is the step, right? So the idea here is if I have a specification and I have a robot that's supposed to satisfy the specification, and the way it's satisfying the specification is by it has a bunch of skills it has. So it develop a bunch of skills, they can come from wherever, whatever you want it to be. And now we're going to see that the task can't be done. All right, so the setup is you have skills. So for example, moving something from one place to another. We have some abstraction. So we are able to take the physical world, the continuous, messy physical world, and create a bunch of symbols, a bunch of kind of, symbols that represent what's going on. So in this case, I mean, there's work, we collaborate with George Gonzalez, and there's other work in the world in terms of, I can take a skill, I can execute it multiple times, just execute it again and again and again. Then create classifiers about what is the precondition, what is the postcondition. These classifiers can act as symbols. So now I know this is the state of the world here, this is the state of the world there. Let me kind of do that. Another way to do it is basically just create manually. You can think about an abstraction as this room, this big conference room, conference hall. This room is one symbol. The hallway is another symbol. I can start moving between them. Okay, so I have an abstraction, and then I have a specification. The work that Adam did was specifically around using linear temporal logic. The linear temporal logic is I have symbols and I have Boolean connected between them, so and or not. And I also have temporal connectors. I can say something eventually happens, something always happens. So I can kind of build specification, I can build requirements from that. German fragment is a specific fragment that has better computational properties. It doesn't really matter for the, I want to give you kind of the intuition of what I mean by monitoring. So the question is, I have skills. I have some high-level task that's written over this abstraction. And the question is, what happens if I can't do the task? So what happens if I'm missing a skill? For example, very simple example, not real, blah, blah, blah. I have, my abstraction is I have this hall. I'm in this room, there's a hallway, there's the hotel, and I have, I want to go to the hotel, and I have a skill that will take me from here to the hallway, but that's it. I just know how to go from here, I just know how to get out the skill. That's it. Right? So I can't get to the hotel, because I don't have a skill for it. So the question is, how do I find those skills? How do I find, in a systematic way, what skill would allow me to do this task? There's a lot of seats here. Just come and sit. Thank you. All of you, sit down. So just to give it what I want to do is I want to give you again a simple example of what we can do with this kind of idea of
Excuse me, the people in the other room are much louder, so I can hear that presentation. So if you could use the mic.
they are loud, aren't they?
Yeah.
Okay, but then I just stand behind the podium, nobody can see me.
long enough.
People. The question is, I have a task, I have a set of skills, I have a set of symbols that allow me to define a task over using those skills, but now I'm on a task that I'm missing a skill, and how do I find that? And I'm not showing you any of the technical detail right now. I'm happy to chat about that, always. But I want to give you a simple example of kind of the combining monitoring, runtime verification with repair. So I'm going to show you an example. Again, all the examples that we show, and I'm the first to criticize myself on that. The example that we show are very simple, right? I'm going to show you something that actually has robots in it, but again, simple. One of the things kind of I'm playing around in my mind these days is how do we make the jump to the not so simple? And that's a big jump. It's a big jump, especially for academics, because we don't have resources, and we have less resources now. If you're in the US, fun times, right? I feel like this would be a good year to go to KTH. Okay, so let me set up kind of the example here. So I have an environment. Actually, let me show you this. This is the environment. And I have a bunch of skills. How do I create these skills? I just manually create them. How could I create them? I could learn them. I could manually create them. Someone, I don't know, those are probably two options, but those are, I don't care. I don't care. Someone gave me the skills, and I know what are the conditions when I can, what are the preconditions, what are the post-conditions? Where can I start from? Where am I going to end up? And it could be non-deterministic, it could be non-deterministic, where the environment chooses. But here, everything is deterministic. So what are my skills? My skills, the robot can move from x0 to x4. It can move from x4 to x0, and it's going to move through the middle. Okay, that's the task. Those are the skills I'm given. It can pick up a cup in T2. It can place a cup in T2. So it can pick up a cup from here, it can place a cup here, it can pick up a cup from the other side, it can place it on the other side, and it can move an obstacle from T1 to T3. Those are all the skills. Are they interesting skills? No. Can I make skills that are more robust than this? Absolutely yes. That is not the point. Okay? The point is I'm trying to show these are the skills I'm given. And what I'm trying to do here, this task is, there's another sensor that says whether the cup is empty or not. If the cup is full, it needs to go to the right. If the cup is empty, it needs to go to the left. And place in T2. Now, it can't place anything if there's an obstacle in its way. So if there's an obstacle in T1, it can move it to the left. Okay? So let me show you kind of, what you're going to see here is good? Oh, sorry. No, I didn't realize it was the audio on. It was not supposed to have audio on. Okay, yes. I will definitely mute it. There we go. I was like, what? Who's talking? Who's talking about me? So what you'll see here is, right now, this is kind of 90 degrees, right? So the left is now the bottom. Did it? Oh my gosh, what I did? It has to come set. Alright. I wonder if I can, is it muted now?
Yeah, no, it's muted.
Thank you. Sorry about that. Okay, so what you'll see here, there's a cup here. This is under Vicon. We know everything kind of, or to me. Oh, what happened? It's under OptiTrack. This is an obstacle. This is the thing it knows how to move. Oh, sorry. This is an obstacle. This is an obstacle. This is the thing it knows how to move. It knows how to move this here. That's all it knows. Okay, so what you're going to see is you're going to see that as it's executing, it's detecting violation of, or it's detecting that it cannot, detecting violation of the environment, detecting things that are happening that it didn't expect. that make it not able to satisfy, to run certain skills. And what you see, this is fully autonomous. And what it's doing is every time it encounters, so this is the monitoring. It's monitoring the assumption as it's going. Every time an assumption is violated, it stops and repairs. So it finds a new skill that will help it continue its task. Okay? And times, this is sped up, and so on. So, but the speed up time is listed there. So it's, right. So now, that's done. Moves it. So now I can't do that skill. I can't move the middle thing. So it repairs it by creating a skill that goes to the right. Okay, now it's going to pick up. So that was violation number 1. It couldn't move the obstacle, the pink obstacle. So now, okay, it's going a little faster than I thought. So there's some violations that are kind of harder to see because the first one, it had to move the obstacle to the left. It knows how to move the obstacle to the left. It couldn't move to the left, so it figured out, okay, I need to move it to the right, and then it put it to the right. Second one is it assumes that the cup doesn't change its status in the middle, but it did. So it changed the status in the middle, and then it created a skill that will go from the middle region back to the table. And now it's going to go back. It's going to try to go back to the other table. And the third violation is suddenly there's an obstacle in the way. So now it needs to kind of create a new skill that will do something symbolically something different. Okay. So what am I trying to show you here? What I'm trying to show you here is the fact that things will happen, some assumption will be broken, and the question is how do I deal with that? So there are 2 things I need to do to be able to deal with that. One thing is to make sure I'm explicit about the assumptions I'm making, so I can actually monitor them. So I can do this notion of runtime verification. The second thing I would like to have some notion of repair, some notion of ability to change or to fix things, right, as I'm going. This was done with the CRL, which I'm not going to go into. And again, this is I always struggle with how much details I want to give versus big picture, and I think this place is kind of like big picture. In general, I like in talks to get intuition, big picture. I'm happy to discuss anything or questions. All right. So the assurances, love the idea of assurances, always with respect to specification. But now we have to think about when we think about safety, especially when I'm very much looking forward to the next talks. What do I do offline? What do I do online? Right? Because the online part, when you think about assurances, typically, in my mind anyway, we think about offline. We think about what can I say ahead of time before I deploy. But these are robots or autonomous systems, and there are things are going to happen, right? And what are the techniques, what are the tools that I can use to have some of the assurances also ahead? So this kind of design time versus runtime, or offline versus online at this point. The final thing I want to push back on, so like half pushing back on, is the comparison to bridges, power plants, and elevators. So I'm gonna push back on that because the specification for these things are very, 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 very well defined, very well defined, and they don't make decisions. Right? So, Bridge doesn't make a decision. If that makes sense, right? When we start talking about autonomous systems, power plant makes decisions. Okay, that's fair. I will accept that. It makes decisions. It reacts to some demand, but those are very, very well modeled with uncertainties, and when we start thinking about autonomous systems, there are people. I guess what I'm trying to say is we have people, right? And when I think about bridges, I think about bridges, okay, yes, there are people going to walk on it. There's a limit to how many people can walk on it. And that's my specification. And I can do things with respect to that. But when we start thinking about the autonomous systems, the type of things we we're in this conference excited about. Because I would argue that the things we can say about elevators, bridges, and power plants are much stronger than what we can say. What we even in the best case, even if we solve everything, solve all technical questions, that's still not gonna. We're still not gonna do it. Okay? And here, kind of, the main thing here is people. People, right? So, kind of, how do we think about these things when these systems interact with people? And environment, and uncertainty in environments, and perception, and all that, but really people to some extent. So this is, we had an actual seminar in 2018, and then, yeah, 2018, bless you. And then from that, we kind of wrote a position paper on formalizing and guaranteeing human-robot interaction. And the question is kind of, what are the how do we think about specifications? How do we think about assurances? How do we think about verification? How do we think about synthesis in the context of human-robot interaction? So I want to give you a kind of a taste of things that my group has done in the context of human-robot interaction, and it's very, and this is with collaboration with actual HRI researchers, so definitely I find it very satisfying and very enjoyable to work with HRI experts. And here are some of the things that we did. And again, Adam's going to show up here again. So what are the things that we're thinking about? So the way you want the thing I want to kind of convey here is there's a lot of research in HRI. There's quite a lot of research in formal methods. And the question is, where do they come from? How do we start thinking about specifications for human-robot interaction? Not just for kind of how are people safe when they're next to a robot, but rather how do they interact in a safe way? What is a specification for interaction? So these are a few things we've done over the years. On the left-hand side, the formalism that we used, the specification that we used was signal temporal logic, the predicates. And there we kind of were able to look at different handover behaviors from the HRI literature and model them using STL. So by changing the formula a little bit, we can get different behaviors for the handover. And we can synthesize, we can generate a controller for a robot arm to do a handover behavior. On the right-hand side, we have this notion of the challenge of social navigation. So if you're walking next to a robot, you don't want the robot to be too close to you, you don't want it to be too far away from you, you want it to kind of match your velocity, you kind of want the orientation to be certain, maybe don't want it to be behind you, maybe next to you, and so on. So then the question is, how do we start synthesizing behaviors for that? In this case, we were using encoding into SMT, which is satisfiability modular theories, which I'm going to talk about. But the thing I specifically liked about this work was the ability to detect when something is about to fail, and basically asking the person, slow down. It's typically because they were walking faster. Or just, yeah, slow down because the robot had a maximum speed. So, or, I'm going to move to your right. Or you can start, when you start encoding these specifications, then you can start providing feedback and increasing the probability of making it more likely for the system to behave as expected when there are things you don't control. Another example is on the left-hand side is work with Professor Laura Week from UC San Diego. And here, so she does a lot of work with healthcare robotics, and especially this was work with, she has a lot of work with around using robots for mild cognitive impairments. In this case, it was, we had clinicians program a robot using LTL, using this kind of tangible programming language, tangible interface. Sorry, they could kind of place things and order things based on these cards, and basically the behind the scenes was LTL. So we were able to synthesize things in this context, in this kind of, what am I trying to say here? What I'm trying to say here, you can use some of these formalisms and some of this spin as the underlying mechanism that allows us to let domain experts program the robots. That's the idea. So anyway, I was going to comment on yet another rejected proposal, but Friday we got a rejection on that. Anyway, NSF. And then the final thing that's kind of more recent is this is using event-based STL, so this is kind of a variant that we created on signal temporal logic. And the idea here is kind of an evacuation scenario. We have a robot. The reason I'm showing you this is because this is outside the lab. This is with a natural perception system. We, using STL, we could define very different behaviors for the robot just by writing a different sentence or writing a different formula. And we can play around with what kind of behaviors the robot should exhibit in kind of this evacuation scenario by just basically allowing us to change things very quickly because it's synthesized from a specification. So this is not so much the interaction itself, but this is a way to facilitate changing the behavior quickly in a way that we kind of have, we know what's going on. So the question that I've been kind of, this is in my mind for the last 5 years, more than that. Well, I guess COVID, so it doesn't count. So roughly 5 years. And we're kind of, there's a lot of work these days I think HRI is blooming, right? And a lot of kind of also coming from learning and from other communities that are doing a lot of HRI, and there are going to be some talks today. And my mind is, how do I write specifications for HRI, right? Because it could be, it could be don't exert too much force. Sure, yes. If it's a physical human-robot interaction. There's also questions of, my favorite example is Todd Murphy's example, in terms of if you have a robot for rehabilitation that helps a physical therapist in a rehabilitation scenario. There's a specification that is assist, but don't over-assist. And how do we start thinking about those kinds of things in the context of specifications? So there are a lot of questions, there's a lot of questions, again, why am I talking about this? Assurances, how do we talk about safety? Like when you have people, what are the specifications? It's not just don't hit something. It could be also don't come too close, don't move too fast. Maybe my definition of how fast you can come at me is very different from my lovely, lovely, lovely 12-year-old boy who doesn't have common sense, right? These are all, what can we do, right? So there's the notion of adaptation, there's the notion of variability. People are different, cultures are different. There are different questions that come from there. And how do we capture these things? How do we specify these things? Okay. So here, you can't even see it. The yellow is it possible? Is this possible? Is it even possible to get to think about at the level of how we think about bridges, power plants, elevators, and so on? I don't know. So with that, let me kind of conclude. So safety. And can you always guarantee it? No, but that's okay. Okay, we're gonna live with some messiness, and the lower, the more contained and more specific we make that messiness, the better. But life is messy. All right, thank you very much. Questions, please.
On the evacuation robot you were mentioning earlier, how were those specifications changed? Were they just was it spoken word? You just typed it?
We typed. So we created 2 different behaviors because one is, in that specific case, the HRI question was, is it better to have a robot kind of follow the person and then when they decide to evacuate, they just guide them to the exit? Or is it good to have like let's say proactive or nudging robot that kind of goes through the exit, and whenever the person's not following it, it goes back and kind of goes back and forth until kind of, and then we create the two behaviors basically by writing two different specifications. And the specifications were almost the same, except for like a few symbols difference between them, and they created very different behaviors. So that's kind of the way we did that.
I'm not too familiar with what LTO is.
Yes, I can talk. Oh, I can always talk about that. I think, like I said, I took out the slide. Okay. If you think about this is temporal logic in 60 seconds. If you think about propositional logic, so you have propositions A, B, C, and then you can think they're true or false, and then you can start thinking about building formulas from there. So like A and B. Is A and B true? Is that formula true? It's true if A is true and B is true. Right? So that's kind of in general proposition logic. I'll give you an example. Hadas in Atlanta, that's a proposition. It's true. Okay, so Hadas in Atlanta and Yana in Atlanta, that's Yana. She's here. True. So Hadas in Atlanta and Yana in Atlanta, true. Hadas in Atlanta or Yana in Atlanta, also true, because an or. Now, that's if you think of the world as static. If you think about the fact that the world changes, the propositions, the truth value can change with time. So Hadas in Atlanta is currently true, but Saturday it will be false, because I'm going to go home. So now I can start thinking about what LTL lets me do is start adding also temporal operators. So I can say some things such as always something is true, or eventually something becomes true, or something is true until something else is true. And I can build things from that. For example, I can say Hadas in Atlanta until Yana goes home. That formula is true. You know, not good on something. LTL is I have these symbols that represent something in the physical world, and I can build more complicated formulas over them that represent kind of requirements over the system. I can build it using the Boolean connectives and temporal connectives to come up with more and more complex specifications.
What does LTL stand for?
Linear temporal logic. So linear. Oh yeah, we can talk more about why linear. It's things about time. Things about time as a linear thing. So something happens after another. There's a different type of logic that looks at time as trees, like branching. But, that was probably too much detail. But linear temporal logic, STL is signal temporal logic, which is kind of, it's not the same. It's LTL is defined over proposition that are true or false. STL is defined over signals. So continuous signals and predicates over those signals. That's kind of the idea. And I'm happy to chat more. Yes?
Professor Hadas, thank you for a nice talk. I also work with repair in the past years, but mainly for repair trajectories when the autonomous vehicles violating traffic rules.
Oh,
So I want to ask a general question because you mentioned the examples, it's kind of environments were updated. Then you try to repair either specifications or the skills. So actually, I think there are different ways you can go, like you can repair environment. So you can also repair robotics, but you can also repair the specifications. So what do you think will be the most promising way to go, like for repair, like maybe in online runtime verification, maybe like some ways are faster than the others, some are more efficient. What do you think?
So, question to you. When you say repair the environment, what do you mean?
You can, for example, like the cup is in a wrong position. You can also move the cup to the correct position by humans, for example.
I see. So human intervention.
Yeah.
Okay. So human intervention will come only if I provide feedback. So feedback is definitely part of the things that I'm interested in this context. And it allows, because I have a specification, I can actually reason about what is broken and then communicate that. And we have some work on that as well. In terms of runtime verification, so let me just kind of correct the terminology. Runtime verification is just the monitoring aspect.
Yeah.
I'm gonna watch and see what happens, right?
Yeah.
There's not one thing that is the right thing, right? I would ideally like to first repair the task, right? Have the robot do what it's supposed to be doing. If I can't do that, I'd like to give feedback. And then either get, you can think about this as different things. I can either I kind of probably want to give feedback anyway, but let's say I can either autonomously fix something to match the original specification. I can autonomously change the specification, which there are techniques out there, there's a bunch of work, definitely not just from my group. Then the question is, do you want that to be autonomous? Do you want the person to know what's going on? So there are philosophical questions, if you will, kind of who does what. And then there's kind of can't fix it, come help me, which is the kind of the third level of how you can repair. So, autonomously repairing the original task, I feel like that would be the best. That's the hardest. Changing the specification makes me nervous because someone wrote the specification. So asking that's kind of where the human intervention starts to come in. So human intervention could be human. Is it okay that I change it this way? That's one thing. And then the lower, easiest, with huge air quotes, is come help me. Right? Do this. So I think they're all important. And for driving, I've not done anything with driving.
I think with driving applications, like the specifications are trivial rules.
Yeah.
Cannot repair trivial rules like simply, right? So it's fixed there. So it's a bit different mindset.
Well, yes and no, because sometimes the traffic laws you have to. You're not supposed to cross a solid line. Sometimes you have to, right? So I'm not trying to. I see what you're saying. I agree with what you're saying. There are some things that are mutable, and there's some things that.
Minimal violation.
So there's notions of minimal violations. There's notion of partial satisfaction. There's all these questions and all these great work out there that are looking at these things. Yeah.
Thank you very much.
Yeah.
This largely extends from your sort of pushback against Bridges' power lines.
Please.
I think especially recently, I'm not huge on safety insurance and my work there. More of my work is on perception and planning. And as I'm sure you've seen it, a big bunch of large language models, language models, and sort of replacing old methods. And so a few places what you talked about today, but I think there might be promise for some of these models. So in my mind, I see environment representations of generating different bridges, different models of the world, using some of those foundation models. And then on top of that, there's what your specifications look like. Are you okay with getting this close to another car? And can you vary that or treat that or vary that? So this might be. I sort of want your opinion or your intuition on this. Is there any promise in introducing foundation models to create specifications, and how much human intervention is needed to monitor that process? Because in my mind, I'm throw an LLM, have it generate a bunch of specifications, could be a terrible job.
Yep.
Humans would have to be wrong, and then we would have to treat this LLM. What does that process? What would that look like to you? And do you think there's a point where we'll be able to scale this entire process and create insurance?
Interesting. So could people hear what the question was? No. Okay. So the question is basically around foundation models and LLMs. And can we use specification? Can we use LLMs to figure out to write specifications? Is that a fair summary? It's interesting because when I think about foundation models, I think about them as replacing the skills. So I have the skills, but the specification is still going to come from someone. So the question of and I should put a plug in, I think Andrew's not here. There's a workshop on Friday about safety of VLMs, vision language models. And if you want to come hear a very opinionated talk, I'm going to give a talk at 4. I know it's Friday at 4, but very opinionated talk. Let's put it that way. So also, I should mention, and I'm productive. I spent last year, I went on sabbatical, I was at Sherlock. So Toyota Research Institute, they're definitely into the foundation models or behavior models. And I find that area fascinating. No cynicism, fascinating. And we don't really know what's going on there. So I think for me, the foundation model entrance into the world, into the deployment world, if you will, would be first let's make them do something useful. And the specifications still coming from people. And as that changes, okay, I don't know, I'm rambling. Actually, you bring up a good point. I see my problem is LLMs hallucinate, LLMs give you crap sometimes, and give me a safe robot with a safe robot. It will be interesting to see how that evolves, and to see if there's anything you can use LLMs to supplement what people are thinking about, or even get the ability to think about more assumptions or more. I don't know. It's a good question. I think to see how things evolve. Check back next. 3 weeks. Check back next year. Yes, that's good. That's a good plan. All right. Thank you very much, everyone.